Hi everyone, and welcome back to our Module 7 lecture series. In this video, we're going to be going over the steps to run a one-way ANOVA in SPSS. So this video will be a great resource for you to refer back to, especially when you're running your activity. It's kind of a secondary resource in addition to the activity video, so that you can cross-check your steps and your interpretations and where to find certain values, etc., etc. For this particular example, I've given you guys a research scenario in which the purpose is that a researcher wants to know if a person's level of physical activity affects their ability to cope with stress in the workplace. Now, similar to our previous examples that we've looked at in this class, I've highlighted the independent variable in yellow and the dependent variable in green. As far as the methods, we have a random sample of 31 subjects who were categorized into 4 groups based on the number of minutes of physical activity they performed. So you guys might recall in like previous discussion posts when I would make comments or feedback on your discussions, oftentimes we can measure a variable. In this case, we could ask people, hey, report the number of minutes that you perform physical activity every week. And then we can sort people into categories based on set criteria. So sedentary would be no activity, low might be maybe they perform 30 minutes to an hour of exercise. Moderate might be an hour to 3 hours, and high might be greater than 3 hours, right? So we can create categories based on certain criteria and then sort people into these categories based on what they report. So in this case, we are dealing with 4 independent groups, or we have a between subject independent variable for our physical activity levels. And that means that people in the sedentary group are not included in any of the other groups. People in the low PA group are not included in any of the other groups, etc., etc. Okay. The dependent variable is or a person's ability to cope with workplace stress, and that was assessed using an average score of a series of Likert items on a questionnaire, which allowed an overall coping with workplace stress score to be calculated. Higher scores indicate a greater ability to cope with stress. All right. When we go into SPSS, similar to when we had our independent t-tests specifically, we are going to want to make sure that we change our independent variable to a nominal status. That way we can have categories. And then we also need to identify those categories where we insert some value and then a label that's associated with that value. In this example, 1 is sedentary, 2 is low, 3 is moderate, and 4 is high. Once we have our data organized appropriately in SPSS and labeled appropriately, we can then look to our task list. Okay, so the first thing that I want to point out is that for our ANOVAs for the next 3 weeks, you guys are just going to assume you have a normal distribution and no significant outliers, as well as random sampling. These are 3 things that are associated with the, random sampling is associated with how you've recruited people. The normal distribution and no significant outliers is related to your dependent variable. And just to limit the number of steps that you're going to be doing in your procedures, we're just going to assume the dependent variable is normally distributed with no significant outliers for all of our groups that we're comparing. The first step is going to be actually setting up the test, and everything else that follows is going to be included in the output. So to set up a one-way ANOVA, we're going to go to Analyze, Compare Means, and then there's a one-way ANOVA. That's pretty simple. From there, we can identify our variables. So typically variables will be included in this box on the left, and then you would just sort your dependent variable into the dependent list box and the independent variable into the factor box. From there, you will click on Options, and that will bring up a pop-up box that gives you some different statistics to calculate. So you will choose Descriptive, Homogeneity of Variance, and Welch. Descriptives will give you your means, your standard deviations, confidence intervals, stuff like that. Homogeneity of variance will give you Levene's test, so that way you can check your homogeneity of variance assumption. And then if for some reason you have a violation of homogeneity of variance, we also will include the Welch's test, which kind of is a replacement for the ANOVA table if you have violated homogeneity of variance. From there you can click Continue, and then that'll take you back to the ANOVA table, not ANOVA table. That'll take you back to the one-way ANOVA dialog box, in which you'll click the Post Hoc button, and then we have two different options, whether we have equal variances assumed or equal variances not assumed. And the reason for this is that this is for our post hoc tests, or like the pairwise comparisons, or basically the glorified little t-tests between each of our independent variable groups that we run if we have a significant effect. So in this case, if physical activity level had a significant effect on our ability to cope with stress, then we would need to look at our post hoc tests to identify where the significant differences are between the groups. So because we have the potential to either violate or meet Levene's test, we need to have post hocs in which we have equal variances assumed, which our choice will be Tukey's post hoc test. And then if we violate homogeneity of variance and we read the Welch's table, and that gives us a significant p-value, then we would read post hoc tests in which equal variances are not assumed, and that will be the Games-Howell test. So once you pick the post hoc tests of your choice, which these will just be the ones that we use for this class, you can click Continue. That'll take you back to the one-way ANOVA dialog box, and then you'll click OK, and that will generate your output. So now that we've set up our test and we've generated an output, we can now check our assumptions. And the one assumption you'll be checking in SPSS will be Levene's test or homogeneity of variance. This will show up in its own table, which is different from our independent t-test, which had kind of the main effect and the assumption test merged together. So look for the table labeled test of homogeneity of variances. You'll see Levene's statistic, and you'll see your p-value for the test. Our interpretation of this is pretty much the same as what we would have used for a t-test. So the null hypothesis is that the variances of each sample is equal or the same. So in this case, we have a p-value equal to 0.120, which is greater than our alpha level. So that indicates that we accept the null hypothesis, which leads us to, in our interpretation, that there are equal variances between our activity levels. So basically what we did is we said for coping stress, calculate the variance for each activity level group, and then are the variances between those groups equal? Okay, so the interpretation would be that we have equal variances. So now we've checked our assumptions, and the next step would be to interpret the ANOVA results. Now, I have two examples for the sake of showing you what the tables look like in SPSS. Given the results of Levene's test on the previous slide, for this example, we have assumed that we have met our homogeneity of variance assumption. So When you meet the assumption, and I have the note up here, right, equal variances has been assumed, that's when you read the p-value in the ANOVA table, and that will be the p-value for the main effect of your ANOVA. In this case, we have a p-value of not 0, but we have a p-value less than 0.001. And remember, the null hypothesis for a one-way ANOVA is that our independent variable has no significant effect on the dependent variable. So in this case, activity level has no significant effect on one's ability to cope with stress. Because our p-value is less than our alpha level, we reject the null hypothesis, and our interpretation would be that activity level has a significant effect on one's ability to cope with stress. Okay. Now, let's say when we looked at our homogeneity of variance assumption, we actually violated it, right? So that means the p-value for Levine's test would have been less than 0.05. So this is the scenario if we had unequal variances. We would then, instead of looking at the ANOVA table, we would look at Welch's test, which is under robust tests of equality of means. Okay, the p-value between Welch's and the ANOVA table test are not, let me start over. The p-value for Welch's test and the ANOVA table will not always be the same. So it is important that you choose to read the ANOVA table when you have met homogeneity of variance, and you read the Welch's test when you have violated homogeneity of variance. The way that we interpret the p-value in the tables are the same. So for our ANOVA table, we said the null hypothesis was that activity levels had no significant effect on a person's ability to cope with stress. For this Welch's statistic, right, our p-value is also less than 0.001, and you'll notice that we have the exact same null hypothesis that's applied to this p-value, and we have this same interpretation coincidentally because our p-value is exactly the same. Okay, so there's two different options to read based on if you have violated or assumed homogeneity of variance. All right, so that takes care of the interpretation of our ANOVA results. And then if you have an ANOVA that has a significant p-value, so a p less than 0.05, that indicates you need to check your post-hoc tests, right? So we've identified from the current example from the ANOVA table that activity levels have a significant effect on the ability to cope with stress, but we don't know which activity levels are significantly different from each other. So that's the point of post-hocs, is to say what are all the possible pairings of our activity levels, and are any of those pairs significant? In SPSS, you should get a table that looks like this. On top, you'll have Tukey's post-hoc test, and you'll recall when we set up the test, Tukey's test was under a kind of a section where we have equal variances assumed, and the game's how test was if we had equal variances not assumed. So again, based on your homogeneity of variance assumption, that will tell you which ANOVA table to read, either the ANOVA table or the Welch's table. And then it'll also tell you which pairwise comparisons to read. So if we have equal variances assumed, you'll read Tukey's test, which for our example, this is the part that we would focus on. And then if we had violated homogeneity of variance, we would end up reading the game's howl results down here. So continuing with what we have so far, we met our assumption. We read the ANOVA table, found that we had a significant effect of activity level on coping with stress. And then because we had equal variances, we will look at Tukey's post-hoc tests. So if we look at this, these are just some highlighted examples to show that there is redundancy in the table. So I've had students in the past where I'll say like, oh, what are the significant pairs of, activity levels, and they will write sedentary and low and sedentary. I'm like, those are the same thing. And you'll notice they have the same p-value. So you only need to list the pair one time. Okay. In this case, that was just for the sake of the example, but you can see there's a p-value column here that we can refer to for our significant pairs. And I would say most of the time I will ask you what are the significant pairs, or that's how I'll phrase it, if any, right? So our significant pairs with p-values less than 0.05 in this case would be sedentary and moderate, right? And we can see that p-value 0.002 is repeated, right? Sedentary, moderate, moderate, sedentary, same thing. And then we also have a significant p-value for sedentary compared to high activity levels, right? And that has a p-value of 0.001. So our interpretation, if we want to kind of combine the pairs together, is that being sedentary causes a significantly different ability to cope with stress compared to both moderate and high levels of physical activity. Okay. We can say that the rest of the pairs are not significant because each of their p-values is greater than 0.05. Right? And again, just to highlight, you would only look at post hoc tests if there is a significant main effect. If you don't have a significant main effect, you just skip over the post hoc tests and don't worry about them, because it is very likely that none of them will be significant. Sometimes we will have instances where the main effect of the test might be significant, but the post hoc tests don't show any significant differences, or vice versa, where you have a non-significant ANOVA, but you have significant pairs. And this happens occasionally, and it's all based off of the estimations that go on within the SPSS software. So if it happens in this class, it's not a huge deal. You kind of just have to know what your differences are and then kind of move forward with that. Okay. For effect sizes, this is like the last part, right? Similar to when we had t-tests, we need to calculate how large the difference is between our means of our groups. So to do this, we were going to refer back to the ANOVA table. Whether you have assumed or violated homogeneity of variance, because this is the only equation that we have to calculate effect size within SPSS. We could calculate effect size going through another test pathway, but I feel like that's a little bit too complicated. So we refer to effect size for a kind of like a one-way ANOVA as omega squared, or this curvy W. Okay. Our effect size interpretation values are different than compared to Cohen's D effect size. So omega squared is calculated differently than Cohen's D. Therefore, the interpretations are different. So when we have omega squared values of 0.01, we consider that a small effect size. If we have omega squared values at 0.06 or close to 0.06, we would consider that medium. And then anything that's 0.14 or larger would be considered large. Similar to Cohen's D effect size, you're kind of just saying, what is your calculated effect size and which of these is it closest to? So it's a little bit more of a subjective interpretation, but usually for the examples in our class, it'll be fairly clear cut what type of effect size you've got. So using this equation, omega squared is going to be equal to the sum of squares of our between groups minus the product of the degrees of freedom of our between groups, so that's this value here, times the mean squared of the within group comparison. And then we divide that numerator by the sum of squares for our total, right, or total sum of squares, plus the mean square of the within group comparison again. So taking the values from this table, if we plug them into this equation, we should end up with a value of 0.416, which compared to our omega squared interpretations, this would be considered a large effect size. Or there is, we could say the effect size is large, or the differences between our physical activity levels is large. All right, so that concludes our example for our one-way ANOVA. In the next video, we will go over the example for reading a two-way ANOVA in SPSS.